Welcome everyone for the fractional calculus seminar series. Today we have Professor Vishal Vasan, who is a faculty member at the International Center for Theoretical Sciences, a center of Tata Institute of Fundamental Research. Dr. Vasan obtained a BE in Mechanical Engineering from Anna University, an MS Mechanical Engineering from Arizona State University, and then an MS and PhD in Applied Mathematics from University of Washington. Dr. Vasan was the S. Chawla Research Assistant Professor in the Department of Mathematics at Pennsylvania State University from 2012 to 2015 before moving to ICTS. His main research interest is in theoretical and numerical analysis for partial differential equations as well as their applications, specifically inverse problems. The application domains include large-scale atmospheric and ocean dynamics, Bose-Einstein condensate, cold atoms, water waves and coastal engineering, growth and its regulation in biological tissues, among others. More recently, Dr. Vasan has been focusing on the theory underlining the data-driven viewpoint of dynamical systems. We are very happy to have you. Professor Vasan, you may please begin your talk.
Thank you. Thank you for that wonderful introduction, and thanks for the invitation to give a talk in this seminar series. So as the title slide says, I'm going to be talking about Markovian embeddings of fractional differential equations. I hope to make the title a little clear what exactly I mean. Certainly a bit of a spoiler, I don't mean embeddings in a very pure mathematical context. I really mean trying to represent fractional differential equations as a ordinary differential equation or a dynamical system in a higher dimension. So this work was done with some wonderful collaborators. Rama Govindarajan is a colleague of mine at ICTS, and Ganga, who's currently a faculty member at IIT Madras, was a joint student between Rama and myself. And Divya was also a joint student between Rama and myself. And Divya is currently at Harvard working with Mahadevan in his group. So the references that this talk is based on are listed here. So Ganga, Rama, and I started working together, and the result of that work was this paper in JFM that appeared in 2019. And many of the ideas that I want to talk about today sort of had their origin in the study of this equation, the Maxey-Riley equation, and especially this particular Bassett history term, and sort of how to develop numerical methods and how to formulate the problem such that one can solve these types of equations. The talk is more or less going to follow the references as listed in this order. So I'm going to spend most of my time talking about the work that we did with Ganga. And then somewhat later, I'll shift gears and talk about this work with Divya, where we really understood sort of what the ideas that were developed in the earlier paper with Ganga, what those ideas were really about. And Divya was kind of instrumental in sort of developing the key notions and sort of expanding on that work. The outcome of that was this nice paper that came out this year, published this year. And separately, Divya also sort of did this application of these ideas to some other systems. I do want to highlight this work because I think it's actually a really nice piece of work. It's an application of these ideas to some specific problems. I'll mention one of them in this talk, but I think the other reason I wanted to mention this work was this is really what's giving the title, in a sense, of the talk today. Okay, with that, I want to move on to a disclaimer. I am not an expert on fractional differential equations. I don't claim to be one. I have not worked much on fractional differential equations, and I certainly don't know a lot of the literature. So apologies to those of you in the audience who certainly know more than I do. And if I miss out some references or if I misspeak, that's entirely my fault and certainly not my collaborators. The other thing I'd like to mention is my main interests are usually sort of developing numerical methods, algorithms, and so on. And that's sort of how I got involved in this particular work by having discussions with Rama and Ganga about the kinds of equations they were solving and sort of how to develop numerical methods for those type of things. I am less of an expert on the actual physics of the problem, and I know there's some interesting, outstanding, and difficult questions surrounding the physics. I'll try to answer them the best as I can, but I'm certainly not an expert. Okay, with the disclaimers out of the way, let's actually jump to sort of the motivating problem for, at least for me, to sort of get involved in fractional differential equations. And that's this equation that was derived by Maxey and Riley together and separately by Gatignol in both happened in 1983. And it's the equation for the motion of a particle that is embedded in a fluid. So you've got this viscous fluid all over the space, and a particle is embedded in this fluid. And this red line here is just showing you sort of how the trajectory of the particle, how it's moving. And the blue lines are showing you how the fluid is moving. So imagine that there's something like a turbulent flow and a particle sort of jostling around in the flow. The position of the particle is given by this x bar. The velocity of the fluid at the location x is given by u bar. And w is really sort of the slip velocity. It is the difference of the velocity between the particle and the flow, right? That's almost by definition from this equation. And it's really the slip velocity, the differences in the velocities that drive the motion of the particle. The second equation is an equation that you can derive more or less from Newton's law of motion by doing essentially a force balance, and you get an equation for the derivative of the slip velocity in terms of other parameters. The term alpha is usually called the Stokes drag. These other terms on the right-hand side sort of come from the fact that the flow is a nonlinear flow. U varies from location to location. There are other terms that are called added mass effect and so on and so forth. I don't really want to get into the details of the equation, nor the non-dimensional parameters, which are interesting in their own right, but are not the focus of the current talk. The focus of the current talk is actually this term, which is this integral differential term, this half derivative, those of you who recognize it as a fractional derivative. This one arises from the fact that the flow has, quote unquote, a memory. Essentially, a particle creates a disturbance in the flow, and then the particle can move into the region of the disturbed flow caused by another particle or by itself. This is the kind of non-local in time origin of this particular term. The equation was derived with this term in 1983, and quite often this term was neglected in simulations, largely because of how difficult it was to handle this term and the unavailability of sort of numerical methods at the time. There are other additional corrections you can do to these equations, but they're irrelevant for the current talk. So what makes the Maxey-Riley-Gatignol equation hard? Well, the presence of this particular term essentially causes you to have to save the state as you do the simulation. So if you imagine trying to compute this term, you need to do this integral in time. And to do this integral in time, you have to save w at different times in the past. So in order to make one time step in the future, you need to know w from 0 to t. And of course, as t increases, the memory cost increases because you have to keep saving more and more. The computational cost also increases with time. Essentially, the length of this vector is increasing, and so the computational cost per time step increases because the length of this vector increases. There is a singular integral. It's weakly singular, but nonetheless it is singular, and that can cause traditional numerical methods based on, let's say, Riemann discretization, Riemann sum discretization of this integral to really fail. So something smarter has to be done. And there are methods in the literature, and in a sense, what I'll talk about today is something that adds to that conversation. The other thing to keep in mind is that this equation as written is not a dynamical system. By that, what I really mean is if I gave you x and w at one time, you cannot evolve the equation to find x and w at another time. All of this is just really due to this non-local term, all these difficulties, and this non-local term is what really makes this not a dynamical system. Sometimes people refer to this as the memory term. Sometimes I may refer to this as the non-local term. In the fluids literature, this is called the Bassett-Boussinesq term, or the Bassett term. There was a very nice review article that Divya wrote about sort of the history of this particular term, when you can neglect it, validity of various numerical methods, so on and so forth. So if you're interested in sort of knowing more about this particular model and what problems this term causes, this article in 2023 is quite a nice review. Refers to a lot of the known literature at the time. So what do we know about this equation? Well, surprisingly, it was only in 2015, Farasman, Haller, and Langlois, Provencher showed local and global existence. So it's quite interesting to note that the equation was derived in 1983, and it was only in 2015 that people actually obtained existence theorems for the mild category of solutions. Strong solutions are not known to exist globally, largely due to the singular structure. The proof is actually surprisingly involved and delicate. It uses some very delicate estimates. And unfortunately, the proof itself does not lead you to a numerical method immediately. Nevertheless, they did prove some very nice results regarding the long-time behavior of the system. So we do know a fair amount of things qualitatively. Quantitatively, in order to do numerical methods, there have been a number of schemes that have been developed specifically for this equation. I mentioned Daiche and Bombardelli as sort of representative. There are many others. Surprisingly, the fluids literature is not as well aware of sort of the broader literature on fractional differential equations and numerical methods for fractional differential equations, which, whilst doing this project, I sort of learned there are certainly a lot of papers out there. One of the papers I just want to highlight is this paper by Garappa, and actually several works by Garappa, which were quite influential for me personally to sort of develop ideas on numerical methods. As I said, there's a lot of debate about whether the non-local term should be there, what form the non-locality in time should take, the kernel of that nonlinearity, the singular structure of that non-locality. All of these things are still, in some sense, matters of scientific discussion and debate. Sort of my contribution really has been a numerical method that is sort of very rooted in a thorough understanding of what the mathematical structure of the problem is, so that people don't have to make some of the arbitrary approximation schemes that are prevalent in the literature to sort of aid the discussion and debate. And I'm certainly happy to have a discussion about the importance of the term, but like I said, the talk will mostly be focused on the mathematical structure. So here's my main message as far as the paper that came out in 2019. Instead of thinking about the equation as sort of a dynamical system or a differential equation or a fractional differential equation, you want to rethink the entire equation as being a boundary condition. to a diffusion equation or a heat equation. So the fractional differential equation itself will be regarded as a boundary condition to the heat equation. So the first thing perhaps I want to motivate is why should the half derivative have anything to do with the heat equation? So if you just play a simple formal game, if you think of the half derivative, its definition being the composition of two half derivatives should be a full derivative. That's almost by definition. And if we just replace this symbol, half derivative, by another symbol, call it ddx, what you end up writing is essentially that the second derivative with respect to x of a function should equal the time derivative or the t derivative of the function. And of course, if you stare at this, you immediately realize what you've just written down is the heat equation. So it seems to be that formally, the half derivative has something to do with the heat equation. We can actually be a lot more precise. You can write down the heat equation for the positive half line. You can give yourself an initial condition, which is 0 throughout. And you can give yourself a boundary condition. So here I'm prescribing the value of Q, that is the Dirichlet boundary condition, on the half line. And if you solve this PDE using your favorite technique, you compute the x derivative at x is 0. That is the Neumann condition corresponding to this Dirichlet condition. And lo and behold, it turns out to be precisely the half derivative operator. So this formal calculation is sort of realized more rigorously as being a fact that the operator that maps the Dirichlet condition to the Neumann condition is precisely the half derivative on the line. Okay, so what do we want to do? We want to change the Maxey-Riley-Gatignol equation to a heat equation boundary value problem. So what I've written at the top is essentially the simplified version of the Maxey-Riley equation. So ddt of the position is the velocity, ddt of the slip velocity is given by these terms. N is just going to represent a generic local in time nonlinearity. All the non-locality is stuck over here. And at the bottom, I've written the heat equation on the half line with 0 initial condition. And the first thing to do is to essentially say the slip velocity in the Maxey-Riley equation will be identified with the Dirichlet condition of the heat equation. So there's the connection between the Maxey-Riley equation, Maxey-Riley-Gatignol equation, and the heat equation. We're basically going to say that the slip velocity, the thing that's in the non-locality, is essentially the Dirichlet boundary condition. Now, when you make that, essentially the second line is a restatement of the Maxey-Riley-Gatignol equation. So notice we had a gamma times the half derivative, and the half derivative essentially gets replaced by the Neumann condition. The minus sign comes from a convention, and you sort of can see that. So what we now have is a heat equation with a boundary condition which is nonlinear, right? So on the left-hand side, it looks like some kind of generalized Robin condition. If I didn't have the time derivative, it would be a Robin condition. With the time derivative, let's call it a generalized Robin condition. But the right-hand side itself depends nonlinearly on Q. So what you really have is a nonlinear boundary condition for the heat equation. The boundary condition depends on this quantity x, and x itself is related to the Dirichlet condition. We have our initial condition, and this statement over here just enforces the initial condition of Maxey-Riley itself. For Maxey-Riley, Q is actually a vector valued system, but for the purposes of this talk, if you just prefer thinking of Q as being scalar, nothing will go wrong. The main upshot of all of this is what's happened when we've done this is that as far as the Q equation is concerned, this is a dynamical system, right? It's the heat equation with a nonlinear boundary condition. everything is local in time. So we've mapped a fractional differential equation to essentially a PDE boundary value problem. Those of you with a physics background would sort of recognize this idea of converting non-locality into a field operation. There's a lot of similarity there. Of course, one of the prices you pay for making it into a dynamical system is that the state vector is now sort of a larger vector in dimension. So previously, it was just position and slip velocity. And now we've got this new object Q, which is also part of the state. So you need to tell me the initial condition for Q, as well as initial conditions for these two to actually time evolve this equation. Since Q is a function, what we've essentially done is we've got an infinite dimensional dynamical system. But Q is a function of X for each T. So we actually have an infinite dimensional dynamical system. So one of the things that was beneficial out of this sort of process of converting this fractional differential equation to a boundary value problem for a PDE was that we were actually able to find some specific solutions and special cases where in all these cases, the nonlinearity takes a simpler form, and this turns out to be a linear boundary value problem that you can actually solve. Those of you who have heard of the unified transform method or Foucault's method, that was the main tool that we used when n, this nonlinearity is 0. You can essentially use this to solve. You could use the Foucault's method to solve the equation. That was what was done in a variety of situations. So in the first case, we had a particle that was just sedimenting under gravity, and our real contribution was a sedimenting particle sedimenting under the force of gravity, but with this non-local in time term. So the gamma represents the correction one gets to the typical terminal velocity of a particle falling under gravity. So the typical terminal velocity is something like g over alpha. This pi comes from a normalization, I guess. And what we found is that there's a correction to this non-locality, and it's actually polynomial in time. So this was, as far as I know, sort of the first explicit such solution that people found. Another thing that you can do is you can take a particle in a time-dependent flow field, but spatially uniform. That somewhat simplifies the equation into something that you can once again solve by hand. And here's just a plot of the velocity of a particle with respect to this oscillating background flow, where the background oscillates with frequencies 0.5, 1, and 5. That's what the 3 different lines are. And then the dashed line is when you neglect the non-local term, the fractional term, and then the solid line is when you include the fractional term. So when gamma is non-zero, it's when you have this solid line. So it certainly affects the motion. The velocities seem to be dampened out when you add the non-local term. And this could have some physical relevance depending on the kind of application we're looking at. We also actually threw in a particle in a plane Couette flow. Turns out that's also an example of a problem where you can solve these equations explicitly. In a Couette flow, this capital N turns out to be a linear function of x. So the whole problem is still linear in all the variables, and you can use different methods. We used, again, the unified transform method to find the solution. The formulae are a little sort of unwieldy, but so that's why I didn't put them on the slide. I encourage you to look at the paper if you want to see the specific form. But I just wanted to emphasize that having this reformulation allowed us to solve specific problems. Of course, not every flow is simple enough that you can solve these equations analytically by hand. So you need a numerical method. And what we realized is that this reformulation also provided us a numerical method. It also allowed us to construct a numerical method to solve these equations. And the idea of the numerical method is sort of schematically shown in this diagram, where you sort of pretend you know the solution to, you know the initial condition or the Q variable at one time, and then you use that to solve the heat equation forward in time, and then you use that to back out what the Dirichlet condition should be at the wall, and then you sort of iteratively do that. So you have this two-step process where you solve for the Dirichlet condition over a time interval, use the Dirichlet condition to find Q at the new time, and then sort of repeat again and again. The details of this are in our original work. I don't want to get into those details because I think we understand better how to do these things, but it is good to know that that the equations do allow you to actually solve this numerically as well. Very simple details about this. Essentially, everything was done for Chebyshev using Chebyshev polynomials to represent the solution over a window delta t. The original method that we did in the 2019 paper was a fully spectral, fully implicit method. So it involved a Newton solve. So it was that part of the computation was a little more challenging than one would expect. Recently, there was this paper by Urizarna Karasa and collaborators, co-authors, where they actually implemented our algorithm in 2019. And this paper also leads you to an online Python library where the method, our algorithm is actually coded up. So if you want to use it, I do recommend you look up this particular reference where they compared it to different numerical methods to solve the same set of equations. And you can sort of see a cost-benefit analysis, and so on and so forth. Here, I'm just showing you a couple of plots of a very simple-looking, similar-looking type of equation. Here, y is a scalar, has the same structure of Maxey-Riley. F is some nonlinearity. On the left-hand side, it's y squared. On the right-hand side, it's sine of y. And this is just to sort of show you sort of why you might need numerical methods, because the behaviors of these kind of equations is quite dependent on the nonlinearity. So as you can see, when you have sort of no forcing, when f is 0, you sort of just have this decay that's shown by the red line. You can add polynomial nonlinearity, and you don't really change the long-term limit of the solution. So if you want, you can think about the t tends to infinity with a nonlinearity and without a nonlinearity. So in that case, on the left, you see that it approaches the same asymptotic limit. Whereas if you add more complicated nonlinearity, something dramatic, more interesting happens. And I guess, of course, these type of results are hard to prove analytically. So this is just sort of emphasizing why you need some good numerics for these type of problems. So of course, this trick I have of sort of relating half derivatives to the heat equation, you might ask, well, can you generalize this? And there's absolutely no reason to stick to only half derivatives. Let's look at this kind of generalization of Maxey-Riley, where instead of the half derivative, I have a 1/3 derivative. And I'll play the same game. A third derivative operator is something that if you compose 3 times, you should get 1 full derivative. So that looks like something which should have a third order PDE. So it should look something like this. And you can actually do the same calculation that I did last time, where I showed you the Dirichlet-Neumann map was the half derivative. In this case, the map that takes the Dirichlet condition to the first x qx term, that is precisely this 1/3 derivative. So once again, a certain kind of Dirichlet-Neumann map gives you this third order, this 1/3 derivative. You can also do it for the 2/3. you have to be a little consistent about how you define these boundary conditions. There is some subtlety there. I will not get into it, but feel free to ask me later about how you can get these compatibility conditions. Nonetheless, this seems like a game you can play. Of course, you could sort of generalize this to higher derivatives if you want. I'll just mention that, yeah, indeed, you can do this higher general recipe. We never published this work largely because I kind of felt it was a bit clunky after a while for arbitrarily high orders. So if M and N are very large, you really get some crazy looking terms that are hard to analyze by explicitly. But in principle, the idea sort of generalizes. There's some connection to work by Caffarelli and Sylvester on sort of fractional powers of Laplacian and wave operators. There is a connection between this approach and what's going on there. So this is just to say that, you know, I'm certainly not the first person to have said that fractional differential equations and PDEs are somewhat related. Though I guess there's some subtlety in the particular statements that we're making. All right, so there seems to be like a general idea behind all of this, and so, you know, it took us a while to eventually answer this question of what exactly is going on. Why were we able to convert that particular Maxey-Riley equation to a dynamical system? Why were we able to apply that idea to different powers of different order fractional derivatives? What is exactly the mathematical structure that was helping us solve these problems? So at the top, I've written what looks like this Maxey-Riley type equation. And what I claim is that you can write it in a so-called Duhamel or mild form, where chi is this function that satisfies something like chi is like a Green's function, if you will. It solves the linear part and equals 1 at t equals 0. If we didn't have the fractional term, if we didn't have this half derivative, chi would precisely be e to the minus t. Sorry, there's a typo here. This should be alpha chi, not alpha y. This should be chi. So if I don't have this half order derivative, chi is essentially the exponential, and that's how you get this term. But it's also true that even when you have a non-zero gamma, that you have something that looks like a Duhamel form. Now, the interesting thing to note about the function chi, which satisfies the linear equation, is that it doesn't satisfy this semigroup property. So you'll recognize that if this property is satisfied by the exponential function, chi does not satisfy this. The exponential function, in a sense, is the only function that would satisfy this property. And so there's no surprise that chi doesn't satisfy this property. And it's the fact that this property is not satisfied that leads to all the difficulties of it not being a dynamical system and not being able to develop, or the memory costs rising high, the computational costs rising high. So all the things that were difficult about Maxey-Riley-Gatignol are essentially due to the fact that the chi function associated with this problem doesn't satisfy the semigroup property. And that's really the main point. So what we realized is actually there is a particular representation that the function takes in all the applications that we've looked so far, that this particular form of a representation was quite common, and we call this the spectral representation. So if chi is given as an integral of the following form over some contour in the complex plane, where f and g are typically analytic functions, g could also be meromorphic as well. When chi has this particular form, we're able to actually make a lot of progress, and it explains a lot of the calculations that we had done or seen earlier. It's really because of this particular form. And many of the problems that arise from the connection to PDEs also tend to have this particular form. So why is this particular form useful? Well, what you can do is essentially substitute this form of chi into the Duhamel form, rearrange terms, and find out that you can actually rewrite the equation in a completely equivalent form for this quantity h. H is a function of two variables. It's a function of k and t. And as a function of t, it satisfies this particular differential equation where, in a sense, like k appears parametrically, right? So h at different k's are not coupled in this particular case. And h takes this particular form. You can think about this as an ODE for each hk. And the integral of h is essentially the quantity you're interested in, y, right? So what has essentially happened under the assumption that chi takes this particular representation is that we started off with a fractional differential equation, and we have ended up with a essentially an ordinary differential equation, but with this parameter k. And so you can actually start thinking of this as a partial differential equation. It's just that in this case, you don't actually have partial derivatives with respect to k. It's just an infinite family of ordinary differential equations. Note, gamma could be like the real line, in which case this is true for k in a continuum. So k is not a discrete variable. K can be a continuum. And that might pose some challenges from a numerical standpoint. So what we really emphasized in this paper was that this representation of chi is what is behind all the magic that happened in all the other problems. And this is what I really mean by Markovian embedding. You started off with a fractional differential equation, and through a particular form of the non-local term chi, the generator of the non-local terms, you end up with this Markovian system. So let's just go back to the particular case of Maxey-Riley, where we had this half derivative. In that case, chi takes this specific form. So it looks exactly like an integral on the real line. You've got this sort of a Gaussian with a variance of, let's say, 1 over root t. And because of this particular structure, the equation for this quantity h turns into this particular ODE. And there's a specific example that we had for Maxey-Riley. All right. So this, of course, tells you how to do a Markovian embedding. What it doesn't tell you right now is how to do numerics. One could just straight up discretize h in k over the, let's say you use some kind of mapped Chebyshev polynomials, and then compute this integral, you compute this ordinary differential equation, compute the integrals. The main difficulty with a lot of these problems is precisely whether h is actually a nicely integrable function, and the rate at which h goes to 0 as k tends to infinity. So the crux of the details are there. And that's something we do mention in this paper. So in order to get a better numerical method, we came up with the following suggestion. Oh, I see. So, okay. I guess I want to mention that before I introduce the numerical method, in a sense, it's got what we realize is the key assumption is this spectral representation of the solution to the linear term, not satisfying a semi-group property. So long as it satisfied this spectral representation, you could do the Markovian embedding. In a sense, this is not limited to just fractional differential equations. Later on, I'll hope to get to an example where we do have an equation in this kind of integral, non-local in time form, but it doesn't actually arise from a fractional differential equation. So the system has this non-locality in time, but it's arising from some other process, not a fractional differential equation. Nevertheless, that problem does have a spectral representation, and we can do the Markovian embedding. So I want to talk about the numerical method. So let's write the Maxey-Riley equation, or whichever equation under consideration, in this mild form or Duhamel form. Let's assume that the function chi is given by a spectral representation for some functions f and g. What I'll do is I'll split this integral into two integrals, one going from 0 to t minus delta t, and one going from t minus delta t to t, right? So if I'm thinking of applying a numerical method, I'm usually thinking that there is a delta t involved, and it's the fact that delta t is small that allows you to approximate these type of integrals. So since the integral runs from 0 to t, we'll split this integral into two, one which is precisely of length delta t, and one which could be a much longer length. When we split these two integrals and use the definition of chi as well as the definition of h, we end up with the following representation. Y of t is given by this integral of this h function evaluated at the previous time step times an exponential with a delta t times delta t step, plus the same integral but over a much shorter interval. So this is the kind of the second integral is the kind of thing that you could approximate with quadrature schemes, and that would lead to a numerical method. The h function itself has an equivalent representation in terms of itself. So hk at time t is given by hk at time t minus delta t, with again an integral term which you can use quadrature to evolve. So what you find is that you have this sort of setup where if you knew y, or if you knew the if you knew y, you can if you knew y up to time t, you can evaluate this expression to get the next h. Once you have the next h, you can evaluate this expression to get the next y. So notice how there's this kind of staggered, natural staggering of processes where you only need to know things up to the current time. So h at time t depends on y from the previous time step. And then y at time t depends on h from the previous time step. And if you recall, that was actually the basis of our algorithm from the 2019 paper, where we were solving the heat equation, then getting the Dirichlet condition, and then solving the Dirichlet condition. Sort of this step-by-step staggered approach is exactly what's going on. And again, all of that is due to the spectral representation. It turns out, for various reasons explored in this paper, and it's actually beneficial from a numerical methods point of view to work with y and h rather than h alone. The fact that these integrals are over a short period of time allows you to control the error better. And you don't have, and the fact that you have this exponential term, typically gamma is a curve such that this exponential is decaying or can be deformed by steepest descent to a decay curve. So this expression tends to behave very nicely, as opposed to the original expression, which didn't have the exponential. Then these integrals need not behave nicely. So this staggered approach actually has a numerical benefit to actually computing these integrals. So here's some examples. So here is the scalar equation that I just showed to you, but where the right-hand side is just a function of t, not a nonlinearity. So we can explicitly solve this problem, and we can compare that explicit solution with our numerical method. And on the left, you see sort of something like a two-stage Runge-Kutta scheme and a four-stage Runge-Kutta scheme that we developed essentially by approximating these integrals by the usual sort of Runge-Kutta style discretizations. So when we develop a two-stage and four-stage, these are the results. And here are the plots of the error for the two-stage and the four-stage. One thing to sort of note, I guess I'll come to the in the next slide, is that even though there are two stages, it doesn't give you a second order accurate method. In a traditional Runge-Kutta scheme, a second order method, a two-stage method gives you a second order accuracy. Here we'll see that something slightly different is going on. Specifically, a two-stage scheme gives you a first order accurate method, and a four-stage scheme gives you a second order accurate method. And sort of the hand-wavy argument as to why that is the case is because the function chi is at t equals 0, the function chi looks like root t. As a result of which, chi doesn't really have a Taylor series or a series expansion in powers of t. It has a series expansion in powers of root t. And because of that, all the methods, all the numerical methods that you sort of develop, you develop under expansions in powers of root t, as a result of which you lose this the relationship between stage and accuracy. So it's two stages, but they are essentially the second power of root t, and hence it's a first order method. A four-stage method is root t to the power 4, and so that's why it's a second order accurate method. The plot on the right just shows you that indeed we get reduced memory cost, CPU times, and operational costs if in traditional methods where you have to save the previous time steps tend to lead to increase in operational costs, specifically the CPU time. And these plots show you that we are getting the correct order for a local in time type system, which is precisely this delta t to the power -1. Okay, so this is a problem where we knew the explicit solution. Here is a problem where we didn't have an explicit solution. So it's a particle in a 2D Lamb Oseen vortex. And the initial velocity of the particle is not the same as the initial velocity of the fluid at that location. That leads to a certain 1/√t singularity in the solution, which a lot of the traditional methods tend to struggle with, and that's precisely why we did this particular example. Here you can see our errors are behaving as per the expected behavior. We're getting a slope 1 and slope 2 for our 2-stage and 4-stage methods. This is a problem where we didn't have an explicit analytical solution. So of course we did the traditional thing that you do in a lot of scientific computing. We did a very high resolution simulation with a very small delta t, and sort of that's our proxy for the true solution. Okay, so I want to move on to probably my final example, where Divya and her collaborator, Rahul Valani, did a bunch of these simulations of basically Markovian embeddings of systems with non-local structure. So what's the system that we're talking about here? It's the system that was discovered by Yves Coudet back in 2005. This is something like a Faraday Faraday wave setup, where you move a bath of water vertically up and down. So you change the gravity or the acceleration due to gravity sinusoidally in time. When you hit a certain resonant frequency, Faraday instability occurs. But if you're away from the Faraday instability frequencies, all disturbances on the surface sort of die down and you get this beautiful flat surface. However, on this beautiful flat surface, if you were to throw a small droplet of the fluid, it can actually bounce on the surface of the fluid without ever coalescing with the bulk fluid. If you haven't seen these videos, I do recommend you search online and watch these videos by Yves Coudet. So Yves Coudet, John Bush, and many others have developed models for the position of such a bouncing droplet on the surface of the fluid. And that satisfies some equation of the following form. So the acceleration has this drag term, and then there's this non-local term. J1 is the Bessel J1 function. and C1, C2 are two positive constants. What you notice in this particular problem is it's non-local in time, but also a non-linear non-locality, right? So previously we had the half derivative as our non-locality, and the half derivative is a linear operator. Here we have a non-locality which is actually non-linear. Nevertheless, the Bessel J1 function does indeed have a spectral representation that's given here. And once you use this spectral representation, you can turn this non-local integral differential equation into a Markovian dynamical system for two quantities, a velocity of the particle and something like the same h function. And so once you see that, once again, we have been able to sort of map this non-local equation into a local in time equation at the cost of extending the size of the dynamical system. Notice how here the curve in the complex plane is different. It's a bounded curve. That actually makes much of the numerics much more stable and much easier to do. There is some issue with this 1 minus k square in the denominator, but there are good numerical quadrature methods that can handle such things. And since k only takes finite values, this equation behaves somewhat differently and better than the Maxey-Riley equation. The equation for the droplet is known to have a chaotic regime as well as a non-chaotic regime, and the numerical method seems to perform just as well in both regimes. So with that, it actually brings me to the summary of my talk. I wanted to sort of emphasize this PDE FDE relationship. I think a lot of people know about this, but I hope to have sort of given you some insight as to what that connection is and where it comes from, and sort of how that connection can actually be used to solve problems both analytically as well as numerically. And one of the key things that we found is that the importance of this thing called the spectral representation. So when you do have functions which do not satisfy the semigroup property, the second best thing, I guess, is that they have a spectral representation. And when you have a spectral representation, you can both get a Markovian embedding, but that immediately also allows you to develop numerical methods. So with that, I'll end my talk. And if there are any questions, I'm happy to take them.
Thanks, Vishal, for the nice talk. Are there any questions? Please raise your hand. I'll call out your name in the order they appear on my screen. Equally, you can unmute your mic for any questions.
Okay, maybe I just then have a comment.
Yeah.
Mm-hmm.
First of all, thank you very much. Very nice really talk. I really enjoyed it. Very nice theories that you developed. I might just comment about this Markovianization. I just wanted to stress that this, as general, this is in fact very well known and used idea in fractional calculus, of course, yeah. And for example, so in my papers and books, I permanently so use this thing.
Yes.
It can be used in a very elementary way. Yeah? So if you look at the fractional, basically, fractional derivative equals to something, yeah? If you turn this from the left to the right, then you directly get this Markovian generator, and you turn your equation fractional into boundary value problem with an increased dimension. Yeah.
Yes.
But you offer something more possibly non-standard, so to say. Yeah. So you do the same idea, but in some kind of original way, which was very interesting, as well as your sort of spectral representation. And possibly another comment also that now some people are developing, for example, sort of me as well, the numerical methods for fractional based on probability. So if you use if you see that all your basically generators, they are generators of Markovian processes, Levy process, for example.
That's right.
you can get probabilistic representation for your thing and use Monte Carlo. So I suppose it would be a good idea to try on your level. So, for example, I never seen this equation, which is very interesting, but definitely this probabilistic method would work as well, and one could compare sort of what probability gives and what your deterministic method.
I really like the comment about the probabilistic methods, because one of the things that I understood from sort of working in these type of problems is sometimes there's a lot of modeling uncertainty. And one way to sort of address the modeling uncertainty is you actually do work with probabilistic methods. Sort of you can then give more Bayesian interpretations and of your solutions. So I think that's a very nice comment. Thank you for that.
Okay.
Are there any more questions? You can you can unmute your mic and go ahead. I have one or two curiosities, but very trivial, because I'm still learning particle methods and things like that. So in the case for the droplet, you have a kernel which is other than the fractional. How did you came across this kind of an operator? Did you construct it, or was it somewhere in the literature already?
Yeah, so the equation for the droplet was developed by John Bush from MIT and his collaborators, I believe. It comes from the modeling of sort of the influence region of the fluid surface onto the particle. So every time the particle falls on the fluid, there are waves that are set off on the fluid surface. And if you imagine sort of a membrane, like a drum, and what kind of shapes a drum would take if you beat the drum in the middle, then you sort of are solving something like the wave equation. And so then it's not surprising that you would get the Bessel function. It comes from assuming some kind of axisymmetry kind of thing. I don't know if that answered your question, but I think that's where it comes from.
I see. I see. I'll look into their study to have to understand more of it. But what is the explicit form of that kernel? You had a spectral representation of it, so I'm not sure if there is a explicit form of the kernel or no.
So the explicit form of the
yes.
So the
Okay,
kernel,
I see.
So the kernel is the J1 of x of t minus x of s. So that's inside the argument of J1. And then you've got this exponential discounting as well. So if this particular kernel, if you want, think of it as a function of x of t, x of s, t, and s.
Okay.
Right?
Okay, now I see the next line. I see the next line.
Yeah.
So that's what I was wondering. So one very trivial question, because I'm not familiar with this numerical technique. So I see that you're using one space variable, but extending to 3 spatial dimensions is fairly straightforward, right? Or if there is any difficulty.
So it really goes to, so the reason you have this extra k dependence here is because the integral in the spectral representation is with respect to that variable. So if you have a spectral representation that involves 2 parameters and you have to integrate over a 2-dimensional region, then you'll get a function h that is a function of 2 parameters.
2 parameters.
So that really comes down to what is the structure of your spectral representation.
Fair enough.
And by the way, I mean, these spectral representations, they don't get really taught in graduate programs nowadays. But I mean, this is what the handbook, NIST handbook, and Abramowitz and Stegun is just full of, right? Integral representations of special functions. That's what all of this is really about. The spectral representations for the half derivative, 1/3 derivative, all of that comes from essentially PDE theory. It essentially maps for Dirichlet-Neumann, generalized Dirichlet-Neumann operators. All of those things are also sort of things that are relatively well known in certain circles, but not popularly known across the board. In the PD examples, for sure, you will always get spectral representations for linear constant coefficient PDEs, because that's what the solution to a linear constant coefficient PDE looks like. So that's sort of why the spectral representation naturally arises. It's also why we call it a spectral representation. Like, we're really thinking K is the spectral parameter of a PDE.
Fair enough.
Yeah.
Fair enough. So one final curiosity. I was looking for papers where Maxey-Riley equations were validated against some experimental studies, and I was finding it very hard to find a paper, because for any equation, the numerical solution, you would compare it to some experimental studies. So are there any references that you would know about it?
So I would go to this reference.
Okay. They have done the experimental validation of the equation.
They have experimental validations. There's also a follow-up paper with more experimental and theoretical simulations. I think it's Daniel Rubrecht, who's the PI in this group. But yes, do look up this, where they do some experimental. They get particle image velocimetry data and match it. I should also mention my own student Divya. Divya has also done work with
PIV.
Well, she worked with an experimental collaborator who Beverly McKean.
Okay.
Who had done some PIV PIV experiments, and she did these comparisons of the flow field with and without the fractional term, as to whether the experimental data was able to capture or would needed the fractional term. So that's there in Divya's work.
Okay.
If you go to you can do a
Okay,
Google
with
search.
particles, but yes, with particles, right?
Yes, there is. So the PIV particles are not the ones you assume are following Maxey-Riley. You assume that they are mostly Lagrangian. But there are additional particles, larger particles, who you actually are trying to model. And so the PIV is just to get the flow field.
Okay, but that's the part I want to understand. Particle motion is what Maxey-Riley equation is all about. So
yes, there is a regime. It's a regime, right? So you have the Maxey-Riley is derived under low particle Reynolds number and low Stokes number.
yes, that's correct. That was the other comment of mine as well. But I see in the community, people don't really seem to bother about it. They are using it for high turbulent flows, but which is not the case. It's literally written in the paper of.
So I believe that flow can be turbulent. It's the particle Reynolds number that has to be small.
Yes, but the particle Reynolds number will be also high if the turbulence Reynolds, because what you're gonna use, right?
You don't.
It's the interaction with the interaction with the scales of turbulence.
You use slip velocity.
No, that's correct. Yeah, that's correct. But it will be the interaction with the scales as well.
I think there's the 2019 paper I might reference some, as well as this paper really gets into the details of the scaling of the various parameters and under which regimes you should use different models. So Divya actually spent a lot of time in a thesis sort of trying to figure out the correct parameter regime under which this is valid and what the physical scenarios look like. And the flow can, in fact, be turbulent. It's just that the particle has to be much smaller. So long as the particle only sees smooth velocity fields, it doesn't matter. But that's the essential argument.
No, with the Reynolds number increasing, the Kolmogorov scales are going to be so smaller as well. So at some point,
Particles are sub-Kolmogorov.
okay, you're really that small.
Yeah.
Really that small. So it's
Yeah. And there are physical applications where that is the large expectation. So we haven't added things like buoyancy and thermodynamics, but the growth of cloud condensate nuclei
mhm.
is happening at much smaller scales. Much smaller scales.
But wind erosion won't happen at those smaller scales. Sand particles would be a bit larger than that.
Sand is
But
different. Sand is different. I'm
sand,
talking about cloud
cloud
condensate.
particle. Okay,
Cloud condensates inside the cloud.
I see.
Inside
I
the
see.
cloud. Yeah.
Fair enough.
I believe there's some folks at Arizona State who have done some very interesting simulations about sandstorms, and there's some very non-trivial behavior happening there.
I see.
Yeah.
I see. All right, that's pretty much all from my side. Are there any more questions? You can unmute your mic and go ahead. Probably no. So this is a good point to stop the talk here. Thanks, Vishal. It was actually very nice having you here, and it was a good discussion too.
Thank you so much. Thank you. This was really good. Thanks for the invitation.
Yes, it was our pleasure.